All right. Okay. So great. I think, again, like always, so screen is okay right now. You guys see it properly?
Yes.
Cool.
Yeah, we can see it.
All right. So we have our session number 8. Again, I cannot thank you guys enough for being present every single time. Yeah, I mean, it is a labor of love for us. It's not that we have to do this, and I'm just absolutely amazed, and I'm not flattering you guys that you make yourself available at these odd times. And yeah, so let's see if we can make good use of the time. We'll definitely try to end at 9:35 today. Okay, cool. So I'll just do a quick recap. We have now a firm notion of what the limit of a function is. We worked out some examples that showed rigorously what the limit of a function might be. The epsilon delta limits can get tricky, but that's the kind of rigor we need. It's somewhat unfortunate, but I think it is absolutely needed. We have stressed this point where, rigor and creativity, they don't have to fight with each other. And there are several examples of this in all of science. One of the glaring examples of this is really the great physicist, Michael Faraday. There are many, many stories available about his experience with, or his rather challenging experience with mathematics, but he was a physicist of first rank, one of the most productive experimental physicists of all time. So, Maxwell came along and he provided the mathematical rigor that just vindicated that Michael Faraday was right. So, we just need to do this. You guys should definitely explore limits on your own. We have not covered all the standard textbook techniques for finding the limits. If we have time, we can definitely do that. And I by no means I want to suggest that that is just a procedure. All these extensions, the techniques, the development of techniques are very, very interesting. One such technique is the so-called squeeze theorem. Have you heard of this thing called squeeze theorem? Basically, if you have a function which kind of gets squeezed between two functions. And this is where, like we were saying in one of the previous sessions, the inequalities become really, really important for us to reach some kind of a conclusion. What I like about squeeze theorem is that you start with an inequality and then you arrive at an equality. That's just beautiful. So if we have time, we can go into that. Here is a problem for you to solve. If you have a pen and paper handy, you can write this down. Limit as x tends to infinity, x upon x plus sine x. Now, we know that Apurva talked about the function sine 1 by x. Here is another function, right? X upon x plus sine x. And I want the limit of this function as x tends to infinity. Now, just think about it. Spend some time if you have some spare time during the week, and we can discuss this next time. Okay. Did you get the function right? X upon x plus sine x. That's all. And I want to find the limit of this function as x tends to infinity. Then we looked at Fermat's technique, another mathematician of extraordinary creativity. we also looked briefly at how Descartes tried to improve upon that technique. One went for the tangent, another went for the normal, and there was a personal rivalry between these two mathematicians, but they were just great. Today we are going to do some more historical excursion. Today's session, I'm hoping, would be really, really fun. We are going to cover a lot of ground, and I just want you to suspend your disbelief. Just imagine that we are on the back of Buckbeak. If you guys know Buckbeak from Harry Potter, and then we are going to cover this landscape, which is really very entertaining, enchanting. There are some really exciting ideas here. Some of them may not be novel ideas to you, but we definitely will look at them in novel ways. So let's start. Right. So let me start with this question. The simplest figure to determine the area of, since the time of Greeks, is what? Which geometric figure Greeks, even Egyptians, thought that was the simplest to calculate the area of?
A square.
A square. Makes sense. Just there are so many ways of looking at it. You can just say that, let's say there is one line that is standing on its point, and you want to find out the number of lines that will be there in a square. You can also think of it as a number of unit squares which are contained in the bigger square. There are several ways of looking at it. But this question that you are right now seeing in front of you, that is the determination of the area of a closed curve, surprisingly often comes up in practice, right? I mean, that I have got some kind of an area enclosed by certain lines, straight or curved, and I just want to find out the area of that enclosed figure. You can appreciate that this kind of a problem comes up surprisingly often in practice, right? I mean, we want to determine the areas of farms, we want to determine the areas of shops, and anything that you can perhaps measure. Areas are simply ubiquitous. Now, look at this one. I want to construct a square with an area equal to that of a figure bounded by a curve. So you are given a curve which is bounded by certain lines. Can you construct a square whose area is the same as the area that you are seeing? Now, this is such a simple question, but the answer is not so straightforward. And this particular process of doing just that, the process of constructing a square with an area equal to that of a given figure, is called quadrature. Now, this word is really very important. Quadrature, again, like I have said in the beginning, words and their origins are really important. Quadra means square in Greek, right? So quadrature is just the measure in terms of a square. So this is what ancient people, medieval people, and even modern people, I wouldn't say that, but they all tried to entertain themselves. They looked at a closed curve, and then they tried to find out a square whose area is the same as that of that figure. Now, I'm going to ask you a difficult question. What is the simplest figure that comes to your mind when you're thinking about geometric figures? Sort of, ideal kind of figure that people have touted it to be an ideal figure. Of course, that is a circle, right? Right. So, it is, just the round figure you see in nature. It's all over. You see, look at the night sky. You see the full moon on the full moon night, and you say, oh, everything is round. And I think, that's the idea. So the question also arose that, this question was really troubling to people, that I want to find out a square whose area is the same as a given circle. We can spend time doing this, try to look at it from the first principles, look at what we have done in these discussions and see if you can have a square that is having the same area as that of circle. Point, food for thought. But now what we are going to do is we are going to look at some other kind of figure. The figure on the right hand side of this, it's also as simple as a circle. Circle is perhaps the simplest, but I can argue that this particular figure is also very simple. What am I going to do here? I'm taking all the points like B, right? And I'm constructing ordinates which are equal to the square of the abscissa, or I take the x coordinate of B, square it, and erect a line, and whatever are the endpoints of those line segments, I join them together. What is this? You obviously know what this figure is, right?
A parabola.
A parabola. So we all, this is what we know, but now here, look at the question that really troubled this mathematician whose name was Cavalieri. Cavalieri, an Italian mathematician, in 1639, almost 400 years ago, was just obsessed with this question. Like we start, the question that with which we started. What is the quadrature of this particular figure? You might, just, I'm walking you through history because I want you to see the struggle that these people went through. I want you to be kind of familiar with the words, the language that they used. So this kind of a thing that I want to find out this particular area, like in this case, let's say ABC, right? Where AC is the part of the parabola. I'm going to call it the quadrature of parabola, right? So once you understand this language, maybe things will become clearer if you are reading history of mathematics and just trying to ponder about all these problems. Now, this is a, I really don't want to give any answers. Like I have said, and like we have always experienced, all of mathematics is problem solving. You just look at a particular problem and try to solve the problem, and then try to piece it together, and then maybe some unifying principle comes along. We call that set of unifying principles a theory, right? So so look at what Cavalieri did. He was imagination is it's really flowing freely here. Look at the part on the left hand side, right? This particular part. You can see that just imagine that A, B, C, and D, A, B, C, D is a square. Okay. And I construct a cube making ABCD as the base, right? I can easily see that this is the back face of the cube ABRS. And now just try to kind of compare this figure with parabola. You can see that J is any point on the diagonal BD, okay? And HJ is just a segment on which I'm going to construct a square, right? So JPQH or HJPQ is a square, right? Nothing fancy here. And what I'm going to do is that I'm going to slide this point from D to B, right? As a result of that, this particular plane, the square plane, will sweep what kind of three-dimensional figure? Are you able to visualize? See, this is all about visualization. I'm sure that you're able to visualize this. What is the three-dimensional figure that the square like HJPQ going to sweep as you go from point D to point B along the diagonal of the square? Am I making it clear? Just tell me if this is clear to you. Yes? No?
Not fully.
Okay. What is it that is not clear? I'm going from the point D to point B along the diagonal, right? And I'm constructing a square. So for example, if the J point would be closer to D, I would have a smaller square because the square's edge will be like a smaller or shorter edge until it goes from point D. At the end, it will be this particular square when J coincides with B. Am I making it clear?
Yeah, but what exactly do you mean by sweep? What area does sweep or?
No, what volume does it sweep? See, you can imagine that, just imagine this kind of square being erected with one point being on the diagonal, like the point J. J starts with A, then it moves a little, gives a smaller square, then it goes again, moves, then it goes to B finally, at which point the square coincides with ABRS, that square. So am I making it clear? Are you able to visualize a three-dimensional figure?
Yeah,
that
yeah.
Nice. What do you think it is?
It's a pyramid.
Very good job. So is everyone able to see this pyramid? What is the one face of the pyramid will be ADB. You can see that, ADB will be one pyramid, one face of the pyramid. ASD will be another face of the pyramid. ABRS will be the base of the pyramid. Are you able to see this? With some effort, I believe you should be able to see this.
Yeah, definitely.
Right? It's like a pyramid which is lying on one of its face. This is not exactly like a pyramid that you have been able to see, like, the Egyptian pyramids.
I just wanted to confirm it's not a symmetrical pyramid, right? It's kind of with one side flat, but it's a geometrical pyramid, right?
Correct. Yeah, it's just a pyramid. Yeah, you're right. So the point D is not exactly above the midpoint of the plane ABRS. That's pretty clear, right? I mean, so it's like, that's what you're right, Arav. So, you know, basically it's lying flat on its one of its triangular faces, right? The ultimate shape of which is ADB, right? ADB is the, so it, maybe I should have done this figure a little bit more, but I was short on time. But I'm hoping that you will be able to see this. What Cavalieri argued was that the volume, make no mistake, the volume of this pyramid is the exact same as the area under parabola. In other words, the volume of the pyramid is equal to the quadrature of parabola. Look at this, like, startling insight. This is just amazing. Why is it true? Look at the right figure, a times a, you know, that's the ordinate of the point A, right? On the right hand side parabola. Are you able to see that? A square. The point B is x comma 0. Are you able to see that? Sorry, a comma 0. Right? On parabola, the coordinates of point B are a comma 0, right? Because it is at a distance A from C, which is origin. So the coordinates of the point B are a comma 0, right? Small a comma 0, right?
Yes. Yeah.
Right. And the coordinates of A, the uppercase A point, are
a comma a squared.
very good. A comma a squared. Is everyone able to see this? I must ask this. I mean, you know, this is really important. Is everyone with me on this one?
Yeah.
Right. So now see what is happening here. See how your imagination is important here. He said that I want to find a geometric equivalent to this. So he constructed the figure, and the figure on the left hand side is just a three-dimensional equivalent of the two-dimensional equivalent that we have on the right hand side. Are you able to see the equivalence between the two? All he did was at a particular point, he just constructed a square. And as the point J slides along the diagonal from B to D, a pyramid gets swept. This is really very sweet. And so now what is the deal? Do you see the argument? What I'm trying to impress upon you is that if you had become Cavalieri, you would have argued exactly the same way. See, Jean Piaget said that to understand is to invent. So if you understand this, there is a very good chance that you would have invented this yourself. I want you to convince yourself. Just see this the way Cavalieri saw, and you know, we all have. That's what I meant when I sent that message, that, you know, this kind of creativity, the flashes of creativity are there in all of us. And so I really like, you know, I see this is beautiful. Are you able to see it with the same excitement that it is the same figure? But now, you know, you might have been told that, you know, how can an area be equal to a volume, right? Area is a two-dimensional thing, volume is a three-dimensional thing. But what Cavalieri's point is that the values have exactly to be the same, right? I mean, the units of volume are going to be different. The point here is that the magnitude of the volume of the pyramid is going to be the same as the area or the quadrature of the parabola. This is just nice. This is just beautiful, right? You know, it's so natural that, okay, all I'm doing is, instead of having an ordinate a squared, I'm constructing a square whose side is the same as the distance of the point J from the left-hand edge AD, right? That's all I'm doing. And that's exactly like, it's almost like looking at this pyramid from the right-hand side. Right? If you look at the pyramid from the right-hand side, like, just imagine that you're looking perpendicular to the edge BC at this figure, this three-dimensional figure on the left-hand side. And what will happen is that if you plotted that area as the ordinate, you will see that all these endpoints, like the point A on the right hand side, we'll arrange them on the parabola. This is just beautiful. I hope you're able to see this. Okay, so that's what happened. And now then what happened? Does anyone know the area of the pyramid? If I am trying to create this kind of pyramid from a square, what is the volume of the pyramid? See, Greeks had, they were very comfortable with straight edges. They had difficulties with continuously varying things like parabola. But do you see, if you are able to imagine how many such pyramids will fit in the cube that is enclosing? What is the volume of the cube if the side is A?
A cube. So will it be 3 pyramids?
Right. So, I mean, very nice. Like, say, I cannot explain. I don't want to spoil it for you. You have to see it. Make an attempt, open this, I have sent the pointer to the slides. Just draw it yourself on GeoGebra anywhere you want. Just draw it with paper and you will see that there are such 3 pyramids that fit in this cube exactly. So what is the volume of the pyramid?
A third of the volume of a cube with the same side.
Right. So it is 1/3 of A cubed. And I want you to just sever at this result. This is just beautiful. I mean, we started with area, quadrature of parabola. We ended with volume of a pyramid. Wow. I mean, I just like this one. Okay, so I want you to enjoy this one. We'll move on to another real beauty. Okay, let's just go on this one. Here is another question related to quadrature. In this figure that is drawn to scale. Okay, it is drawn to scale. If you have, you're projecting this on your screen, just make it maximum, the biggest screen, the full screen. And it is drawn to scale. If the area under the curve AB, okay, listen to the question carefully. This is a really important one. Area under the curve AB. So AB, not the straight line AB, but along the green line AB, BEEP. So, you see that figure on the one side of which there is a curve and all the other 3 lines are straight lines, right? I'm saying that if the area under the curve AB is same as the area under the curve BC, what is the function? See, y is equal to f of x. Now, this is a difficult question. I don't expect you to answer this question so quickly, but just look at the figure first. Look at the point P. Its coordinate is 1. What is the coordinate of E?
R.
2
Oh,
or
sorry.
R. Anything is fine. For now, let's just look at the concrete figures. 2. What about Q?
Are you saying 2 is? Oh, okay, I see.
Q is?
4 or R squared.
Yeah, and G is?
R cube.
Or 8, right? So now, this is so startling. I mean, almost like it shakes you. Amazing. What is happening here is that so first of all, tell me what these points P, E, Q, G, what are they doing? What is the relationship between them? Do you see a pattern?
They are the powers of 2.
Right. They are in what progression, if I were to call it?
Geometric.
They are in geometric progression, right? 1, 2, 4, 8. I couldn't draw 16, but the next point would have been 16. Now, what I'm asking you is a very, very interesting question on the other hand. On these lines, see the first one, PE, the distance is 1, the 1 unit. From EQ is 3, from QG is 4, right? And I'm going to construct an area, or I'm going to draw a continuous curve. I mean, this is just unbelievably beautiful. I'm just drawing a curve y equal to fx, f of x, and that curve intersects all these ordinates at P, E, Q, G at the points A, B, C, and F, right? With me so far?
Yes.
Right? And what I'm finding, or what I'm, telling you, that these areas are exactly the same. A, B, E, P, B, C, Q, E, C, F, G, Q. All these areas and all the other areas, like, if you go to 16, 32, 64, all those areas are going to be exactly the same. This is just mind boggling. I mean, and now my question is, what is y equal to f of x? What function has this capability to render areas like that? They are exactly the same. And I'll tell you one more thing. The area is exactly 1 square unit in this particular figure, because if you see, the point A's y coordinate is 1. So point A is 1, 1. What is point B? Roughly, can you say?
2,
What's the
1/2.
what's that?
2, 1/2.
2, 1/2. How about C?
4, 4.
Yeah. So good job, Shashwat. So so can you now tell me the function?
Is it y is equal to 1 by x square?
That 1 by x square? You need x square
Yeah.
there, y? No, see, B is just 2.5, right?
Yeah, no,
2.5.
it'll be 1 by x, 1 by x.
Right. That's the function. Look at this beautiful function, amazing function, y equal to 1 by x. This function has this unbelievable property that it just gives equal areas only when the x coordinates of the points we are considering are in geometric progression. Look at the equivalence or the relationship between algebra and geometry. This is just beautiful. Okay, so you know, I want you to get a taste of it. Like, try to actually devise the areas of trapezoids. Forget about this function for now, and just let's say that you are actually doing trapezoids. Work out the areas of the trapezoids. This is what mathematicians of 17th and 18th century did. They had nothing. We have GeoGebra and all the tools, but I want you to get the taste of their struggle. Actually find out the areas of these trapezoids. Trapezoid areas, right? There is nothing about it. Parallel sides, add them, half of that times the distance between the two parallel sides. This is very, very clear here, and you will see a clear pattern. This is what these guys did. Okay, the area under this above curve, you know what this curve is now called? Y equal to 1 by x. What is it? This curve is called hyperbola. That was parabola. This is hyperbola. Okay, so this guy, this has this amazing property that was studied by another mathematician, John Gregory of St. Vincent. He did rigorous work on this, and finally he came to an unproven conclusion. By the time he was no more, he had this unproven conclusion that the areas under the smooth curve are the same. Just like what I told you right now, we haven't proved this, right? It's just only an observation. But see, this is how the things start. Like we start observing these things, and then the rigor comes along and makes it rock solid. This is what happens in mathematics all the time, all of mathematics, right? Both the things are equally important. Our imagination, our visualization, our, just breaking the shackles and think about things, make things up, and then put them in a solid rigor. That's what happens all the time. So this is exactly what Gregory did. And we'll move on from this only to sort of build on top of it. Okay, so let's look at this one. Um, uh, Now what I'm going to do is that I'm going to reintroduce you to a technique that you already know. Okay, I'm just going to hold your sort of curiosity and see if I can do a good job of it. Okay, let's look at this one. What do you think of these numbers? What kind of numbers are they?
Whole numbers.
Whole numbers.
Whole numbers. What else? What else is the relationship between them? Is there a relationship? Is there a pattern?
They're all just increasing by 1.
Yeah, so in more algebraic terms, they are in. Is there anything that we know this? Yeah, let me just say this is basically they are an arithmetic sequence, right? The common difference between the difference between any two numbers is common, and they are in arithmetic progression. What about these guys?
They're in a geometric progression.
Right, they are also integers. Very good job, geometric progression. Now suppose that I want to multiply any two numbers. Let's pick 4 and 8 in the geometric sequence. Okay, I'm just going to multiply those two numbers. But I have got a restriction. I don't want to actually carry out a multiplication. Let's say that I want to, you will say, okay, what is this child's play, right? I want to multiply 4 and 8, write this, right? I want to multiply them. Very simple, 4 times 8 is 32, you would say, right? But I'm putting this somewhat artificial, or at least artificial looking restriction that you cannot, or you should not, you must not carry out the actual multiplication and still tell me the result of the multiplication. You can, on the other hand, do addition. So what will you do?
So 4 is 2 to the power of 2 and 8 is 2 to the power of 3. So we can just add the exponents, which is 5, and find the 5th term. Actually, in this case, it would be a 6th term in the sequence, but so which is 32.
Cool. Yeah, I mean, that's a very good observation. So here is the deal, right? What do you do?
Can we use AP?
Yeah, you can, I think whatever I mean, I just want to know how you will do, how will you progress? Now, I mean, yeah, go ahead, Arav, what did you say?
So if we take the first term as say 2, and then after that it's just repeatedly adding to the number of times that we are multiplying it. So if we take an AP with the common difference is 0 and the number of terms is 2, and then we go on adding them by the AP formula.
You can definitely use that, but I wanted a kind of primitive way of doing that. So I think what Shashwat was saying, oh, you want to multiply 4 by 8? Okay, you just first of all there is this first thing that we need to realize. See, this is why we talked about bijection in second or third session. You remember that there is a one-to-one correspondence between these two sequences. There is a one-to-one correspondence. There is a bijection between these two. So I make use of that bijection idea. Okay, you want to multiply 4. First, take the image of 4 in arithmetic sequence. And so the algorithm is very simple, right? Look at where 4 occurs. Go to its correspondence in the green line. Add those two numbers. Then look for the number on the right hand side and then do a reverse way, right? So that's what these arrows actually mean, right? So I think we are on the same page with respect to this, right? So I'm able to do this. And so you guys are perhaps, maybe you have not wondered about it, but there's our sense of wonder is really very important. Why would somebody put such a restriction on oneself? You want to multiply, go ahead and multiply. Why do you want to do this sort of nonsensical thing that, oh, I just want to carry out a multiplication, but don't actually carry out it, but I want to do it only using addition, right? These are all deep questions, right? I mean, they kind of get summarized in our textbooks as, oh, multiplication is nothing but repeated addition. That's true. But the point is that I want you to see these patterns, okay? And a sort of equivalent or an inverse kind of a problem would be like divide 8 by 4 or divide 32 by 4. So you do the exact same thing or in the reverse direction, right? You look for 32, this is 5, look for 4, you look 2, 5 minus 2 is 3, look for 3, which is 8. So that's your answer, right? So just by doing a bijection between an arithmetic sequence and a geometric sequence, you were able to solve some problems. This is still in infancy. We are talking about 1600s or even before that. Okay, so now so far so good, right? So what am I getting at? I'm obviously getting at this relationship, and I think we talked about this a little bit, but this is one of the most potent things in all of algebra, right? It's called the log function, the logarithm function. You can see that it takes in 4 times 8, 32. You pass it to the black box called log, and it gives 5, right? In this particular case, it doesn't matter whether it returns 5 or 15. It just returns a sum number, which is unique. For 32, it will never return any other function, any other number, right? Because it's a bijection, it's a function, okay? Now, if you are familiar with this particular log function, you would ask, what is the one question? I said that, okay, it may return 5 in this case, or it may return 15 or 100. What is it dependent upon? What do we call it?
The base.
The
base.
That's correct. So that's the base of the logarithm, right? So we call it. So the original inventors of logarithm, however, did not talk about this at all, because they did not find any need for it once they devised the problem like this. Oh, it's nothing. It's just the bijection between arithmetic sequence and geometric sequence. Why do you need to know? These sequences are given. Why do you need to know anything, right? So we need to relive those moments, right? So so can you tell me one of the difficulties of this particular technique? What can you not do with this technique?
Like add 4 and 8.
Or, but see, remember, we are trying to multiply two numbers, right?
But okay, but
no, our problem is multiplication. We can always add any number to any number in this, but what you're saying is that the numbers, trying to add the two numbers which don't exist in the green line.
Yeah.
I see, I see. But even more, more fundamental problem. You're right. We can't add the numbers that we don't see. Similarly, we can't, multiply the two numbers that we don't see. So somebody may come along and say, okay, use your technique and multiply 3 by 5. Right?
Yeah.
We can't do
Okay.
that, right?
Uh-huh.
Right? This particular thing.
Understood.
Right? Because that is the basic problem that we are trying to solve, right? This person came along and said, oh, I can multiply any number by any other number by just adding without carrying out the multiplication. And this other person comes along and says, oh, well, that's good, but what is the multiplication of 3 times 5? Now, this another person who invented this technique, their names inventor was John Napier, and Henry Briggs was the one who worked a lot on this thing. And we'll talk about that if you guys are interested in this. Logarithms. If I were to tell you one thing that you should absolutely understand, then that's logs. Okay, this is a beautiful technique in algebra. So now the answer to that question that John came up with, okay, 3 times 5, he said, okay, all I have to do is I have to make sure that I have good lookup tables. All I have to have is the numbers that you normally run into should be in my table. Remember, the left-hand side table, or the entire table in which the left-hand side numbers are all in geometric sequence, right-hand side ones are all in the arithmetic sequence. That's all is needed. And you can do whatever you want. If you guys, any one of you guys can come up with your own table where as many numbers as you can appear, you would have invented logs. Amazing stuff. I mean, this is as simple as that, which kind of gets buried in, log tables, anti-logarithms and these things and that thing. It's just not necessary. We have to see a thing in its true light. This is what Napier did. This is what Briggs did. They just came up with huge tables. The only thing, the left-hand side numbers in geometric sequence, right-hand side numbers in arithmetic sequence. And then, most of the numbers that people ran into were already there. And how they came up with this is the engineering aspect of it. Like, people, they work meticulously on it. We are talking about 1620. In 1620, Henry B. Briggs came up with a table which had 10 digits of precision, 10 digits. Can you imagine this? I mean, this guy spent 20 years of his life just coming up with these tables. He used various techniques to do this. These real heroes have lost their place in history, but fortunately, they have not been. This is why we should learn some bit of history. Okay, so that's what it is, right? So we have kind of, so here is one of the things that Briggs did. What did he do? See, so, look at this. Like I told you that all these things were arbitrary. What is the only thing that is needed? Left-hand side numbers, the black numbers should be in geometric sequence, green numbers should be in arithmetic sequence. That's it. What you assign to them, completely arbitrary. Do what you want. Okay. And now he tried to do this. He had a bijection where 1 goes to 0 and 10 goes to 1. What would be a third mapping? Can you tell me?
100 goes to 2.
Right. That's what it is. So simple. See, I mean, you guys are almost inventing these things. And now he's one thing that Henry Briggs did was this. What about this? See, we did not think about this thing yet. But we are curious. Human beings are curious people. What about 0.5? 0, 0.5 and 1. These are in arithmetic sequence. What is that question mark that will be right between 1 and 10? What will that number be? Yeah, tell me some representation of that number.
10 to the power.
Yeah, go ahead.
10 root of 10 square
Root of 10. 10 to the power 0.5. You just take, somebody just said that, take the number on the arithmetic sequence side, make that a power of some number, and then you will get a corresponding number on the left hand side. And that's how all these things sort of came together. These are all the underpinnings of calculus. Nothing can be ignored. All of these things came together, and now we have this big, extremely useful thing that we collectively call calculus. Okay, so that's what happened. And bricks did lots of things. I really want you, if you have spare time, think about how Briggs would have come up with these things. How would he have constructed his tables to the 10th place of precision? It's just amazing. Okay, we need to quickly move on, but this is really, really interesting. Okay, all right. Now, recall from 2 slides ago that the areas under the hyperbolic curve y equal to 1 by x between the x coordinates and the successive number on any geometric sequence. Okay, I have just recreated it from 2 slides ago, right? So this is exactly again drawn to scale. This curve is y equal to 1 over x. Okay, and you can see that the area ABEP, exactly same thing. I've used the same thing. You guys should really go back and review these slides till the next time. They're all very, very interesting. BCQE, CFGQ, and so on. All these areas are same. Their value is A. Okay. The only thing is that see how things are related to each other. On the left hand, on the x coordinates, now we have all the numbers that are of interest to us right now are in geometric progression. Okay, so now what will happen? Now think about this particular thing. Okay, you can see that relationship between what we have established here and the foundation that was laid by logarithms is very, very clear here. All right, look at the table very, very carefully. The x coordinate, when it is 1, I'm area under the curve from x equal to 1. That's what I'm interested. So obviously there is no area here, so it will be 0, right? And the area under point A is 0. But when the x coordinate is r, which is basically the point E here, right? Right? The area under that is A, right? A, B, E, P. Now, when the coordinate is r squared, this is also A, but I'm considering the area under the curve from x equal to 1. So it will be A plus A, right? Clear?
Just one thing. In the generalization, right, you put at the bottom, r to the power log A. If you're saying it's the x coordinate, it should probably be r to the power log x.
R to the power log
X. Since you're
yeah, no, I mean, I'm just saying that the yeah. I think it should be instead of
or
1,
you can,
1,
or
2,
you can
3,
say
4,
any
5.
coordinate. That's also
Yeah, so I think the point I'm trying to make is that if A is made 1, the big A, uppercase A is made 1, then all these areas will become 1, right? So A will be 1, which means that it will be 0, 1, 2, 3, 4, 5, 6, 7, and so on. The point, however, is that for an arbitrary point, this is what is going to be true. Log A is the area under the hyperbola y equal to 1 by x between x equal to 1 and x equal to A. The point is that the log function makes its appearance here as well. See how the things are related to each other. Okay, that was the point that I think I should make that change. I'll make that change.
Yeah, no problem. It's just the thing that we don't, the A never really comes in this graph, so it should just.
I mean, A comes in the graph because A is the area under the curve, right?
I mean small a. I mean small a.
Yeah, I mean, A is any number. The small a is any number. That's what I'm saying.
Okay.
The point is that here, see, that's a good observation, Apurva. What I'm saying is that, if you want to find out under any point here, not necessarily the points which are 1, 2, 4, 8, 16, and 32, or not only those points, but let's say that 23, right? So 23 is, what is 23? 23 is 2 to the power log 23 to the base 2. That's exactly same as 23, right? So what I'm saying is that if you have chosen any arbitrary point here, then what is the area under the curve? Then it turns out to be that it is log of A. A is any abscissa, any x coordinate. Not necessarily those discrete points that we have. Is that clear?
Yeah. Okay,
cool. All right, so we'll move on. This is the last slide that I have. I think we have, race against time, but I hope you guys are, assimilating all of these things. OK, so I'm going to. This is perhaps something that you guys are familiar with, very, very familiar with, but I wanted to bring this together. I expect a lot of interaction here. Just speak up, OK? Imagine that I'm going from point A to point B. In what? Just look at this figure and tell me that I'm going from point A to point B. But I'm going from point A to point B in what?
A straight line.
A straight line. What else? Yeah, just say the words. Anyway, sorry about that. I think I'm just saying that I'm going from A to B in space. Right?
Okay.
Right. I'm saying that a point is A here, a point in real space. There is another point B in real space, and I'm going from point A to point B, right? In distance, I'm going from, so you can see that this is, how Descartes actually came up with these things. You see, so this thing is a physical thing, right? The distance, the ground is something that is physical thing, like I can kick it, I can touch it. That thing is a physical thing, right? So I'm going from point, let's say from town A to town B. So A and B represent two towns. I'm going from town A to town B, right? Imagine that these towns are 45 kilometers apart. And the road is good, at least initially, and I choose to use my motorbike. I just, I'm going on my motorbike, okay? As I go from point A to point B in space, there is another thing whose very existence defines our own existence that is also changing. That thing that changes is so commonplace that nobody really teaches about that to us. We just sort of have an understanding of this thing that is changing. So my question is here. As what is that other thing that is changing as I go from point A to point B in space?
Time.
Time, right? So the time changes because I'm not able to be at both A and B at the same time, right? It's a famous adage that people say that you can't be at two different places at the same time, right? So that is the time immemorial. Therefore, I can always say that in going from town A to town B, I'm also going from point A in space to point B. I'm also going from some time in, some point in time to another point in time, right? Now consider that I go to a town that is 30 kilometers, a small another point which is a town which is 30 kilometers from point A in half an hour, wait there for 15 minutes, and then go to the town B. After my stop, I take on, I take another half an hour, during which I traverse the remaining 15 kilometers. Is that clear? So you can see that the point A is at 0, 0, point point C is at 0.530. D is also at 30, but its X coordinate is 0.75. And then point B is 1.25, comma 45. Time is measured in hours. Distance is measured in kilometers. Nothing, very dramatic here, right? We all know that my journey can be shown by these discrete points. But I want you to underscore these things. I want you to know that these are the discrete points. Okay, these are really discrete points. You must be wondering, why am I not connecting or joining those 4 points A, B, C, and D? Any guesses? Why am I not doing that?
Maybe because there's no set order in which you go to each place.
Can you explain a little bit more?
Like instead of going A to C first, you go A to B, and then go back to C.
No, but why am I not joining the point? Your impulse would be to join A to C to D to B, right?
Yeah.
If I were to show my journey, see, my question is very specific. When I want to show you my journey, I'm saying that, okay, my journey is these 4 points, A, C, D, and B. These discrete points, proper coordinates, there is nothing here, just 4 points. You would say, no, that's not true. You would have an impulse to join A to C, C to D, D to B, and that's when the journey would be, the representation of the journey would be complete, right? So why am I refraining from joining those lines? Or sorry, joining those points? I'm saying, from what I have told you right now, that I started from point A in time and space. I went to a point B in time and space. I went to a point C in time and space, and I went to point B in time and space. That's all I have told you. So which means that those 4 points is the right representation of my journey, isn't it?
But maybe you went to each point in order, but you don't know which path you took. You took any path, right? You could have taken a straight line path, or you could have taken a curved path, or you could have.
Yeah. Can you elaborate? I mean, that's true. What does that mean? That means that between points A and C, between points A and C, which are again 2 points in space and time, I don't know which other points in space and time I have taken. So I literally don't know, right?
Yeah, so you don't know.
I did not tell you. I did not tell you where I was when, let's say, 5 minutes had passed. I did not tell you where I was when 1 minute had passed. I did not tell you when 1 second had passed. But by doing this that I'm going to do, I'm telling you something more important. I'm making an assertion that all the points that are now these 4 lines are comprised of are the points depicting my journey. Now, this is not an easy point. This interplay between the discrete and the continuous is really central to calculus. Because like you said, Apurva, that, I went from A to C, whether, I joined it using some, sine curve or, sine wave or parabola or circle, nothing. I could have done anything, right? But the straightforward thing for me was to just join the straight line. But joining the points A, C, D, and B with straight lines has implications. Now I suddenly tell you indirectly that when half the time has passed between A and C, half the distance also has passed between A and C. I have come, the distance between C is only half as much as it was when I started my journey by doing this. See, this is not easy. This is an implication of joining that by straight line, right? Is everyone agreeing with me here? By making the number of points infinite. Yeah, go ahead.
Yeah, since you joined them in a straight line, you can say that at half the time you were at half the distance.
Yeah, until I joined that with straight lines, I couldn't say that, right?
Yeah,
I could only say that. Yeah.
You can't say that. You can't say that. Do it the opposite way. Basically, if you say that I was at half the distance and half the time, you can't still say that for like quarter the distance or 3/4 the distance. We don't know the rest of the path you took, but it's because you joined it by a straight line that you can say along each of these points I was at the proportional distance.
Correct. Only because of the straight line, because that came to my mind, but the side effect of that is that I suddenly made my journey a progression through infinite points in time and space. It's just amazing, right? So that's what happened here. And now, if somebody were to ask me how to compare or how to correlate these two things that are changing independently, time is changing of its own accord. Distance is changing because of my doing something. And now if somebody were to ask me how these things are changing at every point in time, then I'm necessarily looking at the concept of what we call a rate of change. Now, if I want to find out what the rate of change is at every point in time, this is how it is going to look, right? Immediately when I start my motorbike, it is moving at a speed of 60 kilometers an hour. But somebody would say, oh, you haven't even traveled for an hour. How can you say that your speed is 60 kilometers per hour? But you know what I'm talking about. I'm talking about the instantaneous speed, like at that point, what is happening. And you can see how the concepts of continuity are now making sense, right? This is exactly what we call math is meeting physics here. Physics is the thing, like, in reality, what is happening. And we make the use of mathematical entities in order to relate these two things together. The green line, the dotted green line, is obviously on the same plot at the same scale, shows us the speed or the velocity of my journey. You can see that the velocity comes to 0 in no time, right? So now, whatever Apuru you had discussed with solid dots and the continuous, and that all that thing starts making sense here. Okay, so you can see how rate of change is important in every physical thing that we do. There is one thing that changes. As a result of that thing that is changing, something else changes, and I want to know exactly what is happening in a rigorous manner. So rate of change is that concept. And now I'm going to show you the last slide. Sorry, I ran over by 10 minutes, but this was needed. So the two things that we saw today, one was quadrature, another is a rate of change. And now we are in 17th century. And it is up to these two men to sort of join these things together. You know, the stage has been set now. Lots and lots of people have contributed to that, and it was up to the imagination and creativity of these two men that we just waited for it to flourish, and that is the thing that we are going to cover in the next discussion. You obviously know the names of these two men, right?
Yeah, Newton
Yes.
and Leibniz.
Yes, Newton and Leibniz. So these are the guys. But see, so many things have happened, and that's about it. I'm sorry, I had prepared for an hour, but it went over. So there you go. I mean, this is what it is. We are perhaps going to put this in a rigorous pedestal next time. But till then, I think you should just sever at this. Please go through the slides whenever you can. Think about these problems, and you know, is there any question?
I just wanted to know a bit about how the log tables were made, because like the way we calculate with logs, where we convert it to the log and then we make an anti-log, how were they exactly made, especially for the trigonometric functions?
No, I mean,
I
see,
had the same question.
go ahead.
Even I had the same question.
Yeah, I mean, see, trigonometric functions, I mean, like we said, right, on this slide, that the log was really a bijection, and it is still a bijection. The only thing is that we now need to know what is called as interpolation. If we know that 2 maps to 1, 4 maps to 2, then 3 should map to some number between 1 and 2, right?
Right.
That much is pretty clear, right? Now, what the idea there is really that of interpolation. We need to find out, we need to make a more and more accurate estimation of the value that is between 2 and 4, which is in geometric progression, with a value between 1 and 2, which is in arithmetic progression. So I'm not going to spill the answer. I mean, I don't want to do that. I can give you the answer, but I want you to spend time on that. You know, I want you to live like what Henry Briggs did. So spend, you know, we can take this up next time again. But I want you to spend time, like, you know, all those log tables were manual labor. There were no calculators around. They painstakingly calculated all these things. And obviously they used techniques. And one of the techniques was interpolation. And the interpolation was, you know, more accurate. Briggs had to come up with these things. And so we will talk about this if you guys are really interested in it. But you can imagine that the constraints are very simple, that the numbers are in geometric progression on the left hand side, arithmetic progression on the right hand side, and try to come up with that. Forget about anything else. You can choose whatever base you want, but these are the things. So, but one thing I didn't understand, Arav, from what you were saying, that you said that trigonometric functions, I mean, logarithms are just logarithms, right? This is just a bijection, simple log function. So I didn't understand. Yeah.
So like in 11th, 12th, for the calculations, we are not allowed to use calculators, especially for the boards. So what they do is they give us log tables. So basically, if you want to say divide two big numbers, it's pretty hard to divide them, 4-digit numbers, for example. So what you do is you convert the numbers to log, then you subtract them, and then you take the anti-log of that. So you get the approximate answer. So how does that work in a way is what I was wondering.
Yeah, no, I thought that you said something about trigonometric functions. I was
so similarly for trigonometric functions, suppose you want to find, say, the sine of 22 degrees, which is a very odd number, but it's all there in the, or you want to find the sum of two sines, something like that.
Correct.
So then you convert it into log, you solve the log equation, and then you use the anti-log to get the final answer.
Correct.
So I was wondering how that works.
So the point is that, again, Henry Briggs did this, and we can perhaps go through the tricks that he used, but I want you to think about it yourself rather than telling the answer right away. How would you really do it, right? I mean, how would you, like we tried with this, right? So for example, what Henry Briggs did was this, right? He said this, and this was the first question that he saw, like, okay, when the power is 1/2, what am I going to do? How am I going to reach the point, the value 3.1634, which is the square root of 10, just by these tables? Right, so first approximation is 5, but obviously 5 doesn't work, right? 5 is not the square root of 10, right? So how do you do that, right? So these are the you will see that you will rediscover that yourself if you used whatever you have seen so far. Like, you can use y equal to x 1/x. You can try to, like I said, a small exercise would be to actually do the trapezoids. Why can't you think? I mean, literally Henry Briggs would go with joining all those points, like these points, right? A, B, C, F, all these with straight lines, and then create trapezoids. The x difference is, that x difference is 0.1, 0.2, 0.3, and then what will happen? You will make a more and more accurate estimation, isn't it? So that the interpolation is what he used for this. But I'm not going to give you the entire answer because I want you to at least do something, try to find out the square root of 10 using that and using whatever you already know. For example, the x equal to a, x to the power a plus times x to the power b is x to the power a plus b. What will you do? Like, let's say that knowing these things, can you do some interpolation? Can you do some interesting tricks there? So something that you can do yourself. And we'll discuss this particular point. Good question.
All right, thank you.
Cool. All right. Any other questions? Again, thank you very much. I thought that we did better this time as far as time is concerned. Good questions. Good session as well. As always. Please, if you have any questions, post them on our group, and we will discuss. Okay. We'll meet next week then. All right.
Yes.
Cool.
Great.
Yes.
I will stop the recording.